Now that we know what a definite integral is, let's talk about different properties of definite integrals. Let's look at the first one. This says the definite integral from a to b of f of x dx is equal to the opposite of the definite integral from b to a f of x dx. Remember, a is our lower limit of integration, or our lower value for x, and b is our upper limit of integration, or our higher value for x. So what this means is that if we switch our limits of integration, the original area from a to b and the new area from b to a will be opposites of each other. Let's look at the second one. This one says the definite integral from a to a of f of x dx is equal to 0. What this says is that if I'm looking for the area under a curve from when x equals a to x equals a, that there is no area. And that makes sense, because we would really be looking for the area of a line under a curve. And because a line has no width or breadth, that means it has no area. So if we're asked to evaluate a definite integral from when x equals a to x equals the same thing, a, that area is always 0. Look at number 3. This says the integral from a to b of c times f of x dx is the same thing as c times the integral from a to b of f of x dx. And this harkens back to our derivative rule. Remember when we were finding derivatives of functions multiplied by constants? We could always pull the constant out in front of the derivative. Well, we can do the same thing when we're working with definite integrals. If we have the integral of a function multiplied by a constant, that's the same thing as pulling the constant out in front of the integral. Property 4 says that if we have the integral from a to b of f of x plus or minus g of x dx, that's the same thing as the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. In other words, we can integrate term by term the same way that we differentiated term by term. And then lastly, if we have the integral from a to b of f of x dx, that's equal to the integral from a to p. Now p is just some point between a and b. So that would be the integral from a to p of f of x dx plus the integral from p to b of f of x dx. So we can separate one integral into two or more integrals by integrating from the left endpoint to some x value between the left endpoint and the right endpoint b. So let's look at this example. Here we're told that the integral from 0 to 3 of f of x dx equals 2, the integral from 3 to 6 f of x dx equals negative 5, and the integral from 3 to 6 of gx dx equals 1. And we're asked to evaluate the integral from 6 to 3 of f of x plus 2 g of x dx. We're given the value of the integral from 3 to 6 of f of x dx, and we're given the value of the integral from 3 to 6 of g of x dx. But we're not given the value of the integral from 6 to 3. We're given the value of the integrals from 3 to 6. So we need to switch our limits of integration to make them match the information that we're given up top. To switch our limits of integration, we have to negate the entire integral. So our new integral will look like this. We negated the original integral, which allows us to switch our limits of integration. And now this expression has the same value as our original expression. We also know that if we're integrating an expression with multiple terms, that we can integrate term by term. Integrating term by term gives us this expression. We also know that we can move constants in front of the integration sign. So let's do that next. That gives us this expression. Now we know that the integral from 3 to 6 of f of x dx is equal to negative 5. That's given to us in our instructions. So we have the opposite of negative 5, which is positive 5. Then we have minus 2 times the integral from 3 to 6 of g of x dx. And we know that the value of the integral from 3 to 6 of g of x dx is 1 because that's given to us. So we have 5 minus 2 times 1, which is 3. So the integral that we were given has a value of 3. This example asks us to use the value of the integral I to evaluate the given integral. And we're told that I is equal to the integral from 0 to 1 of x cubed minus 2x dx. And we're told that that integral has a value of negative 3/4. And we need to find the value of the integral from 0 to 1 of 4x minus 2x cubed dx. Well, 4x minus 2x cubed and x cubed minus 2x are not the same expression, or at least they don't initially seem to be. And if we don't have an x cubed minus 2x, then we can't evaluate this integral. So let's see if there's a way to alter this 4x minus 2x cubed to make it x cubed minus 2x so that we can use that value to evaluate our integral. The expression 4x minus 2x cubed is two terms, and both of those terms have a common factor of 2. So let's factor a 2 from each of those terms to see what we get. That gives us the integral from 0 to 1 of 2 times the difference 2x minus x cubed dx. Now we're getting somewhere. We see that we have a 2x minus x cubed, and our given information contains an x cubed minus 2x, only the signs are different. So let's factor out a negative from each one of those terms now, and see if we can get x cubed minus 2x. And there we have it. Now let's pull the constant negative 2 out in front of the integral sign to get this expression. And now we just multiply negative 2 by the value of the integral from 0 to 1 of x cubed minus 2x dx, which is negative 3/4. And that gives us positive 6/4 or 3/2. And there we have the value of the integral from 0 to 1 of 4x minus 2x cubed dx.